Hi everybody, welcome to the lesson on analysis of covariance, which is also called Ancova. For this analysis, we're going to go back to the first Anova we ran, the one-way Anova. But this time we're going to add something called a covariate to the analysis. A covariate is a numeric variable that we're going to add to the analysis. It's not part of what we're interested in studying exactly. But we think it might have some sort of influence or correlation with the dependent variable. And if you remember, in the one-way Anova, the independent variable is the categorical variable with the factors, and the dependent variable is the thing that we're wanting to compare the means of. So the benefit to using a covariate is that it can help explain some of the variability in the dependent variable, which makes it a lot easier to see what is truly the effect of the independent variable. So it kind of reduces some of the noise in the model. And a lot of times the covariate is a confounding variable, which can strengthen your claim if it turns out there's an effect of your independent variable. It can help strengthen your claim that there is truly an effect by mitigating that effect. An example might be, and the first part of this is just your one-way Anova. So you've got an experiment where people are taking either they're taking a foreign language 2 semesters, either in an immersion program, a fast-track program where you take 2 semesters in 1 semester, or a regular semester sequence of courses where you take 2 semesters in 2 semesters. This part is just our one-way Anova. Now the second part is what makes it an Ancova. We might expect that, if some of the people took the language in high school and still remember some words, or if maybe they've just picked it up here and there from popular culture or whatever, we might expect that if they have some pre-existing knowledge of the language, that might impact their retention of the foreign language. So we might use a pretest as a covariate to help explain some of those results. So let's talk about the assumptions of the Ancova. The main assumption is that the covariate and the independent variable are independent, meaning that they're not related, meaning that there's no difference in the means of the covariate by the levels of the independent variable. And to do this, we're just going to run a one-way Anova where the covariate is going to be the dependent variable. And if we reject H0 in that test, then the assumption is violated. Otherwise, there's not a significant departure from the assumption. There's another assumption as well, which is that if we were to run a regression of the covariate as it's predicting the dependent variable, that the slope would be the same in each of the groups. We haven't covered regression yet, so you get a free pass on that one. We're getting to regression here in a couple weeks. So now let's look at the main test. So if you're in SPSS, we're going back to the general linear model under univariate, and we're going to run that the same way, except we're going to add a covariate. We'll get to that in just a second. Our effect size is the same old partial eta squared, and the post hoc is still under EM means and comparing main effects with the LSD. The least squares difference, not a drug. So an example that we're going to look at is we've got this data set where we want to compare to see if there's a difference in a person's libido based on, and libido is measured on a scale of 0 to 10, where 0 is no libido whatsoever and 10 is really high libido. And we've got 3 levels of the dose of Viagra. We've got a high dose, a low dose, and a placebo. And we want to know, is there a difference in libido based on the dosage that the patient receives? And we're going to use partner libido as a covariate because we think that might have an impact on the patient's libido. And partner's libido is measured on the same scale. So we're going to analyze general linear model, univariate, and we've got dose of Viagra is our factor, because that's the categorical variable that we want to use as an independent variable. Libido is the thing we're trying to predict, and partner's libido is our covariate. We want to see under options the descriptive statistics and the estimates of effect size. So we'll click continue and we'll click OK. And I'm going to go through this output, which I have over here. Actually, before we do that, let's run the assumption. So we'll come back to the main test. I wanted to show you that first, but let's look at the assumption. So to check the assumption, we're going back to analyze, compare means, our one-way Anova. And remember, this time we're looking at the covariate and whether it's related to the independent variable. So here we're putting our covariate in the dependent list. And we're putting libido in the factor. Here we don't need any of the options. So we'll click OK. And there's our output. And I've copied all of this over here. So as usual, we can write on it. So the first piece of output that we're going to look at is that assumption test. And on here, we are interested in the F value and the significance. So we've got P equals 0.158. So there's not a significant violation of the independence assumption. I will not abbreviate that word. Assumption. All right. So we're good to go on the assumption. Now let's look at our Ancova output. The first thing here just tells us that we've got, how many patients in each group. The descriptive statistics can be really useful for us. The main output we need is this test of between subjects effects. So we don't care about the corrected model or the intercept. Let's first look at our, this is our independent variable, the dose. Well, now it's just going nuts here. Sometimes my pen gets a mind of its own. So the dose is our independent variable. And we get our F value here. This is our P value and our partial eta squared. So P equals 0.027 on the dose. So that is significant. And that's the main thing we're interested in. This is good. This shows us that the Viagra makes a difference in libido. And the partner libido is our covariate. And we get that it has a p-value of 0.035. There's its F statistic, and it's got a partial eta squared of 0.160. So P equals 0.035. So we have a significant covariate. Now, since we got a significant result on dose, let's go back and run the post hoc tests. So we're going back to analyze general linear model univariate, and we're going to click on EM means. And we're going to take our dose, move it over, compare main effects, and we want our least squares difference. And then it's going to give us our pairwise comparisons, which I have already copied over here. So our pairwise comparisons show us that there's a significant difference between placebo and low dose. There is a significant difference between placebo and high dose. But there is not a significant effect between the low dose and the high dose. Okay, so these are significant. So P equals 0.593. So the low-high is not significant. All right, so our output or our write-up might say something like this. We always put our sentence in there to start with, explaining what we did. And in this case, we want to emphasize that that this is what we're interested in. We're really interested in comparing the effect of the dosage of Viagra on the libido. We're just, almost as an aside, using the partner's libido as a covariate. So we talk about our assumption of independence. So we don't have a significant violation of the assumption. And I want to point out, because I've seen this in some of your homeworks, be aware of stating this too conclusively. So we've got no significant differences. We can't say that there are no differences across groups, just that there are no significant differences. And then we report the results of our main test. And then again, almost as an aside, we talk about the significance of the covariate. And then we talk about the results of the post-hoc tests. And this time there were only 3 comparisons, so I reported the p-values for all of them. I think the lack of difference between low dose and high dose is actually really an important claim, or at least I'm not that kind of a doctor, obviously, but I would imagine that that would be something that doctors would really be interested in, because that might indicate that a higher dose isn't likely to have much of an effect. So I think that the doctor might be more inclined to give a low dose if that's the case. So I included the descriptive statistics rather than just, stating them all. So that's our write-up. I want to point out before we leave this section that you can also add a covariate to a repeated measures Anova. And that is actually why this is included in a mixed design, because it can be, the covariate is a between subjects. It's not a factor, but it's a between subjects measure. And the repeated measures is a within subjects. You can also add a covariate to a two-way Anova, but I want to say that you don't want to overdo the number of variables in a model. You want to keep it as low as possible while still being able to explain the dependent variable. There's a principle in statistics called parsimony, which is that, simpler models are better, all things being equal. So, and keep in mind, every time you add a variable, you add a possible interaction. So when you add a variable, you're not just adding one variable or one thing to check, you're adding potentially several, depending on how many other variables you already have. All right, so that's it for this section. And, if you have any questions, please feel free to let me know.